Pranav and I worked at Oregon State University with Dr. Pranav as my mentor, and my co-mentor was Daniel Taylor, who's a master's student. And so what I did was Wi-Fi power source design from RF-powered sensors. So basically, anytime you transmit something with a wireless signal, you're sending some amount of power, and that's how something receives a signal. And so what happens if you could just make that power go slightly higher and more power? Now, at some point, you get a bit dangerous, but there's enough power there that you could power something, such as a sensor in a wall. Now, that sounds really weird until you realize the big problem is people don't know if the pipes are broken in the winter. And so one way you could check that is put some sort of humidity sensor in a wall, and then just put your phone up next to your wall, and it just turns on and sends you data, and you can tell, oh no, it's exploded and I need to fix this right now. And so the entire purpose of this project was to see if we could find a way to generate a waveform that we could use to power some sort of sensor. It wasn't really the receiving end. That was sort of a theoretical, we know we can do it, but it's more about how can we use existing hardware, or can we make some sort of code and hardware combination that transmits a certain waveform in such a way that you can actually use it to power something. And so waveforms, fancy things that are really confusing, and actually that has no data at all, that has no value. All that is some sort of LTE waveform. And so wireless technology is based on waveforms, or signals. And so basically what happens is you have your bits of data, and they're translated into sine and cosine waves of varying amplitudes, which are then stuck together. And so if you want to get high power on a sensor, you need a consistent amplitude, and you can see there, it's not very consistent, it's jumping up and down all the time. And so the entire purpose of the experiment was to figure out if we could find a way to force the transmitter to be up as an high amplitude as long as possible, or at least as consistently as possible. And so I used 3 different methods to generate these ideal waves, as we call them. Before that, there was other people who actually did some work before me. And so someone else in Dr. Natarajan's lab tried to use that little guy. That's an Arduino Feather. It's about the size of a keychain, to send wireless signals. It's so small that it doesn't actually have enough power to really do anything. And it was also really not consistent. It just said hi, and then it went away for a good second or two, and then came back again. And there was other similar projects at other universities that we found, but there was not really any good documentation that we could follow, and we wanted to produce our own sort of method. So the first one that first generation method I used was a BeagleBone. So this is a credit card sized computer, and that big silver thing right there, next to the really big black thing, is a wireless transmitter. And so I used Linux to force the BeagleBone to search networks for other devices to connect to every so often. Now that involved downloading a tool, to download a tool, to update a tool, to download something that would let me change one setting. And that took a really long time and a lot of Googling. It was very complicated. It makes me appreciate Windows a bit more. And so basically, what it does is it keeps pulsing through the bands, looking for something to connect with. And so it'll go through all of the normal bands that a computer or a personal computer or a personal device would use. And these bands that I'm talking about are different segments of the wireless spectrum. So in this case, for this hardware, it was 2.4 gigahertz. And I believe there's like 13 different bands. And only 7 of those are actually usable. The pros of this method were it's pre-existing hardware, which means it could be expanded onto some sort of Android device, a PC, or something like that, which means I could literally put my phone up to a wall and see what's behind it. It's also small, and it's much more practical than the other ones. You'll see why in a little bit. The cons are, it doesn't work. It doesn't actually do anything, and the software variables that I was provided by Linux, they don't do anything, and I'll show you why in a second. Right here, we have a graph of what the BeagleBone was outputting. That's 350 milliseconds between each pulse. Those aren't that big of a pulse, and also that's like 20 milliseconds of uptime. And between that, there's about a third of a second, which means you can't get any power whatsoever out of it. And when provided, I think there's like 6 or 7 different variables that Linux provided to me to change with this specific command. And they didn't do anything. They just the same waveform. And as far as we can tell, they changed the name of the device, and that's it. It just does something. The issues that we also run into issues because of the wireless security protocols that are actually baked into the hardware itself. We're not allowed to, by the hardware, to address it, like just send it some bits and tell it, go send me somewhere, because of the way it works. It wants this particular destination or some purpose to it. And that we could not achieve with Linux. So we move to generation method number 2, MATLAB. MATLAB is a really interesting, really cool software programming language and environment that allows you to generate, that allows you to do an analytical analysis of large data sets. Normally is what it's used for, but it can also generate waveforms. It's got a lot of toolboxes for it. And so I use MATLAB to generate wireless signals using a method called QPSK, or quadrature phase shift keying, which is a really long